A long time ago, it is believed that our continentals were once all connected. In 1912, German earth scientist Alfred Wegener proposed this theory that all of our continents were joined. This supersized landmass is called Pangea, a Greek word for all of Earth. Wegener proposed the continental drift theory. He was not the first scientist to suggest something similar, but he was able to support his hypothesis with evidence. That evidence included analyzing both sides of the Atlantic Ocean for rock types, geological structure, and fossils. He noticed matching mountain range and fossils that were on each of these separated continents. Wegener said that the different landmass drift apart and continued to work to find evidence to prove his theory. Unfortunately, he passed away on a mission to Greenland when he was 15 years old. In the 1960s, new research was found to prove what Wegener could not, which is tectonic plate theory. Alfred Wegener was right when he said that the continental were joined, but it was not the continent that drift apart. Instead, what can explain the movement is the theory of tectonic plate. Discovered in the 1960s, tectonic plate is a scientific concept that gives a better understanding of how dynamic our planet is. The Earth is broken into sections called tectonic plates. These plates float along the upper metals. They are driven by gravity. Tectonic plate is always in motion and move about 3 inches per year. They move apart by metal convection or subduction at the plate boundaries where they meet. They are divergent, transform, and convergent boundaries. At transform boundaries is where you will find fault as the two plate sides pass each other, causing massive earthquakes.
Wegener's ideas that support the theory of continental drift are: the continental puzzle shorelines of new maps suggest South America and Africa were once joined. Identical rocks of the same type and age are found on both sides of the Atlantic Ocean. Wegener said the rocks had formed side by side and that the land had since moved apart. Mountain ranges with the same rock types, structures, and ages are now on opposite sides of the Atlantic Ocean. The Appalachians of the eastern United States and Canada, for example, are just like mountain ranges in eastern Greenland, Ireland, Great Britain, and Norway. Wegener concluded that they form as a single mountain range that was separated as the continents drifted. Ancient climates. Ancient glaciers leave gases in rocks after they recede. We see common glaciers exhibited in India, South America, Africa, and Australia. This suggests they were all a part of the same land mass at one point. Wegener used fossil evidence to support his continental drift hypothesis. The fossils of these organisms are found on lands that are now far apart. Coal beds found in North America, Great Britain, and Belgium were deposited during the same time. Wegener supported his theory by demonstrating the biological and geological similarities between continents. South America and Africa contain fossils of animals found only on those two continents, with corresponding geographic ranges. One of these animals, an ancient freshwater reptile named Mesosaurus, could not have crossed the Atlantic Ocean. Instead, Wegener proposed that the animal lived within the rivers and lakes of a singular landmass which later broke apart. Other fossils evidence also support the theory of continental drift. The earliest marine fossils found along the eastern coast of South America and the western coast of Africa date from about 150 to 2,000 million years ago, suggesting that the Atlantic Ocean did not exist prior to that time. Ancient rocks on the Brazilian coast also match those found in West Africa. Evidence of glaciers is present in regions with warm, dry climates. This indicates that continents that are close to the equator today were once closer to the South Pole in the distant past. Coral reef and coal-forming swamps are found in tropical and subtropical environments, but ancient coal seams and coral reef are found in locations where it is much too cold today. Wegener suggested that these creatures were alive in warm climate zones and that the fossils and coal later had drifted to new locations on the continents. Grooves and rock deposits left by ancient glaciers are found today on different continents very close to the equator. This will indicate that the glaciers either formed in the middle of the ocean or covered most of the earth. Today, glaciers only form on land and near the poles. Wegener thought that the glaciers were centered over the southern land mass close to the South Pole and the continents moved to their present position later on.
The main reason that Wegener's hypothesis was not accepted was because he suggested no mechanism for moving that continents. He thought the force of Earth's spin was sufficient to cause continents to move, but geologists knew that the rocks are too strong for this to be true.
Okay, we move to the third question, which is what are the evidences that support the theory of plate tectonics. Okay, first, all magnetic objects on the earth are affected by the earth magnetic field. Second, when rock cool near the surface of the earth, they record the magnetic field that exists, the normal or reverse polarity. Third, at the mid-ocean ridge, paleomagnetic investigations show alternating bands of normal and reverse polarity, so the spread of the sea floor generated by the pattern. Fourth, at the mid-ocean ridge, new sea floor would be produced and destroyed in deep ocean trenches, according to Harry Hess. Fifth, the sea bottoms edge corresponds to the pattern anticipated by the sea floor spreading. First, at the mid-ocean ridge, the sea bottom is the youngest. Second, with increasing distance from the mid-ocean ridge, the sea floor becomes older. So lastly, the evidence are the pattern of the global quiz left and corresponds to plate boundaries on the right image.
Earth is divided into 4 layers, starting at the center, from deepest to shallowest. They are the inner core, outer core, mantle, and crust. Firstly, the inner core. The radius of this solid metal ball is 1,220 kilometers. It is made largely of iron and nickel and is extremely dense. The planet's inner core spins a little faster than the rest of it. Secondly, the outer core. This section of the core is formed of iron and nickel as well, but in a liquid state. This liquid, which is heated mostly by the radioactive decay of the elements uranium and thorium, turns in massive chaotic currents. Electrical currents are generated as a result of this motion. Next is the mantle. This is Earth's thickest layer, measuring over 3,000 kilometers deep. It is dense, heated, and semi-solid, and it is largely made of iron, magnesium, and silicon. Last but not least, the crust. The crust is mostly made up of light components including silica, aluminium, and oxygen. As a conclusion, the lithosphere, the uppermost section of the mantle layer, and the crust combined is divided into plates that move across the asthenosphere, the molten upper layer of the mantle, according to plate tectonics theory. The plates move relative to each other at varying speeds ranging from 2 to 15 centimeters per year due to the convection of the asthenosphere and lithosphere. These plates will eventually converge, pull apart, or slide past one another. The majority of earthquakes and volcanoes are caused by these activities.
Some of the most dramatic changes in the Earth crust, like mountain ranges, new islands, or earthquakes, occur along the plate boundaries. There are three types of plate boundaries: divergent boundaries, convergent boundaries, and transform boundaries. Convergent boundaries occur when two plates collide. There are three major types. First is continental to continental. This occurs when two plates of continental crust collide. They buckle and thicken, and this causes a mountain to form. Next, you have continental to ocean collision, when a plate of ocean crust collides with a plate of continental crust. The ocean crust is more thick and subduct or goes underneath the continental crust. The magma from the melted oceanic crust rises to the surface, and this results in volcanoes along the boundary. Ocean-to-ocean collision occur when plates of oceanic crust collide. The older, more dense plate subduct under the younger plates, and as a result, the crust melts and creates an island arc. Next is divergent boundaries. This is when two plates away from each other. The separation allows the asthenosphere to rise toward the surface and partially melt. This melting creates magma, which erupts as lava, and then the lava cools and hardens to create the new rock and ocean floor or new continental crust. That's the crust and upper part of the asthenosphere cool and become right rigid. They form new lithosphere like mid-ocean ridge. Most of these divergent boundaries are located on the ocean floor. However, rift valleys may also form where the continental are separated by plate movement. And finally, transform boundaries occur when two plates move past each other horizontally. When the plates move next to each other, they do not go along smoothly. Instead, they scrape off each other in a series of a sudden slippage as a crustal rock, and this can be felt as earthquake, unlike the other types of boundary. Transform boundaries generally do not produce magma, and the San Andreas Fault in California is a major transform of boundary. So there we go. Three types of plate boundary: convergent, divergent, and transform.
There are three examples of a tectonic plate movement. The first one is a convergent boundaries. The second one is a divergent boundaries. The third one is a transform boundaries. The first boundary is a convergent boundaries. This convergent boundaries occurs when the tectonic plates are moved towards each other or strike to one another. When the plates strike to one another, it can cause earthquakes, volcanoes, and also a deep trench. There are three major types of convergent boundaries. The first one is a continental and continental lithosphere. The second one is an oceanic and continental lithosphere. The last one is an oceanic and oceanic lithosphere. The oceanic continental convergent boundaries occurs when the oceanic crust subduct underneath the continental crust. The oceanic lithosphere has a greater density than the continental. As it collides with the continental crust, it abducts underneath the continental lithosphere and as it sinks, the magma is formed and may begins to rise up to the surface and form volcanic mountains. And also earthquakes may be occurs and the deep trenches may be formed. When the oceanic lithosphere collide with the oceanic lithosphere, a similar events occurs. And also the last one is when the continental strike with the continental lithosphere, neither crust abducts or magma, and also earthquakes may be occurs. The example of the convergent boundaries is where plates serving land masses collide. The crust crumples and buckles into a mountain range. India and Asia crashed about 55 million years ago, slowly giving rise to the Himalaya, which is the highest mountain system on Earth. As the mash-up continues, the mountains get higher. Mount Everest, the highest point on Earth, may be a tiny bit smaller tomorrow than it is today. The last one, at ocean and ocean convergence, one plate usually dives beneath the others, forming deep trench like the Mariana Trench in the North Pacific Ocean, which is the deepest point on Earth. This type of collision can also lead to underwater volcanoes that eventually build up into island arcs like Japan. The second example of a tectonic plate movement is a divergent boundaries. The divergent boundaries occurs when the huge of a tectonic plate move away from one another. This occurs above the rising convection currents. The rising magma push up on the bottom of the lithosphere and flow laterally beneath. And this laterally flow cause the plates to move in a opposite direction. The divergent boundaries are a constructive boundaries because the new crust is formed. As the new plate move apart, the molten magma is filled up and create a new crust. There are two types of divergent boundaries. The first one is a continental and the continental lithosphere. The second one is the oceanic and oceanic lithosphere. The oceanic and oceanic divergent boundaries occurs when the two oceanic move away from one another. This is where a sea floor is spreading away take place. The most common example is the mid-ocean ridge, which stretch around the world. And also the Red Sea is example formed by the divergence between African plate and Arabian plate. The last example of the tectonic plate movement is transform plate boundaries. The transform plate boundaries occurs when the two plates are sliding past each other. When the plates are rubbed against each other, it can cause a huge stress when the position of the rock can break and resulting in earthquakes. The example of a transform boundaries is found in the San Andreas Fault in California. This can cause intense earthquakes, linear valleys, small ponds, and also a deep trench.